How did it go? There you go.
Alright, so let me get straight to this. This is chapter 3. This is Bernoulli's equation. And almost all of Bernoulli's equation implements this. Let me give you this picture reminds me of problem I was once posed. The problem that was proposed to me years ago is there was a very tall, slender building, and they wanted the outside, or how about we say conservative, estimate of the pressure load for 100-mile-an-hour winds. And that's about 150 feet per second. So we'll just say it's 150 feet per second. So winds blowing at this thing straight at it, what's a conservative estimate? What I mean is, what's the maximum load? Now, what will happen is, and we'll just go back and take a look. This was actually a real problem that I dealt with. Now I'm going to make things up. I'm going to say this is 10 foot wide and this is 50 foot. And so you want to know the worst case load. So if it's 150 miles per, or 150 feet per second, and it's got an area of about 500, how do you determine that load? Well, let's look at down on it. So we're looking down at this object. Maybe I'll move it to the side a little bit to give myself a little bit more room. Looking down at this object, air is blowing at it straight. Now what will happen is all these particles are coming at it. Nothing is going to go through it. The one that sits right here, it'll be what's called a stagnation point. And think of it like this. There are places in which you might see water, stagnant water going against something. And if you put a particle there, it'll just sit there. The neighboring, what it'll do is go around it. So in fact, these other particles will go around this thing. Now, in the effort of turning these particles, the pressure is higher here, but it will not be as high as the stagnation pressure. So what I did in this particular problem is I said, well, what if this stagnation pressure is distributed across the whole surface? That would be a very conservative estimate, because the stagnation pressure is the highest pressure you can get. And so let's look at this. P plus gamma z plus rho v squared over 2 is equal to a constant. And let's see, just out of curiosity, let's do a stop, and at this point, since I'm going in here, I'll go ahead and do the word of the day for fluids, which is where we are. Okay. Really strange the way this is. Fishing at atu.edu. Trucks. What is the truck? Come on. Well, did I not get it? There. Okay, I just got a post. I better check the stream. I did not check the stream to help with the stream on the receiving end here. Okay, seems like it's okay. Yeah, let's just look up the density of air. Now this is pretty good. Here's what I'm going to do. I'm going to convert this. I'm going to convert it in an interesting way. Okay, so it says the density of air 15 degrees at center is about 1.225. Hey.
I just had a note to put some back
Oh.
to the class.
Oh, okay.
They're having ACTs in here tomorrow, so
Oh,
we
okay.
got set up for them.
Oh, okay. I was wondering what's going on there. I was like, okay.
Yeah, well, I usually, if there's nobody in here between classes, I usually try to clean these boards.
Oh, oh, okay.
But,
Okay. So I'm going to do something really strange. That will give me 1.225 kilograms meter to the cube over 1,000 kilograms meter to the cube, because that's what that is. So this is a very strange way of doing it, but this is a way you can do it to eliminate the dependency on units. 1.225 divided by 1,000. 2 zeros and then a 1. And that has no units. So now, if I want to know the rho of air over rho of H2O, you just take the specific gravity, multiply it times the rho of H2O. That gives you specific gravity, which is this number, times now my new rho is 1.94 slugs per cubic foot. Why? Because this value and this value are exactly the same thing. And this value has no units. Therefore, I can just take it straight over, multiply it times that, and I'll end up with 0.001225 times 1.94, or 1.94 gives me the density of air of approximately 2 zeros, 230,765 slugs cubic foot. That's way, way tinier than what water is, because water is 1.94. Now it turns out I don't need this, but if you needed to know that, you would multiply this times 0.001225 times 62.4 and carry out that, but I don't need to know that. So here's the deal. What does Bernoulli's equation tell you? It says pick a point, say 1, pick another point, say 2. P1 plus gamma Z1 plus rho V1 squared over 2 is equal to P2 plus gamma Z2 plus rho v2 squared over 2. What is interesting here is stagnation means the velocity 2 is equal to 0. So I want to just draw this over. Now the elevation, in other words, we're going to assume that the wind comes this way and that there's a line here of points that kind of stagnate, and the one that goes neighbor to it goes around. So this means they don't go up and they don't go down. This means the elevation of point 1 is the same as the elevation of point 2. These cancel. So what you get is P1, well, actually get P2 minus P1. I'll take this, move it over, equals to rho times V1 squared over 2. So now let's go through this. The change in pressure, the delta P, which is what this is, would be, now, let me see if I can copy this down. 0.00237, 0.00237, copying the density, 65 times 150 feet per second squared over 2, and this is in slugs per cubic foot. Numerically, I got that number. I'll just keep that number, and 150 squared by the 2, 26.736. 26.736. Now, look at what these units are. This is a slug, foot squared, foot to the third, over second squared. At first glance, that's an annoying unit until we realize that F is equal to MA gives us, if we want to eliminate this slug, we can say slug foot second squared in a pound. So if I want to get rid of that, take the second over, pound second squared over foot, take that in there, and get a pound second squared over foot. And then I say cancel these out, and I got a foot on bottom and a second squared on bottom. And now I get pounds per foot squared. Now if it's 26 pounds per foot squared, and it's 500 feet squared, 26 pounds times here. This is a conservative estimate because actually 13,000 pounds. This is a conservative estimate that this item that's sitting here will have a load that the sum total is 13,000, and assuming it's uniformly distributed down 13,000 pounds, pushing the wind pushing. Now the reason it's conservative is because, as we talked about before, this is the highest pressure that you can obtain, stagnation. If you move a little bit to the left of it, the pressure drops. So if you were to plot the pressure here, you would probably find something like this. Well, this would be your 26, and these would be smaller. So, alright, let me put the screen on that thing. So, what else can you do with this? Okay. Here he talks about normal to the streamline, and then there it is again. Now let's look at, let's take a look at this one. Okay, so if we zoom in and take a good look at this, there's something interesting that occurs here. The particles are moving from left to right. If this is well machined, meaning that it does not, let me see if I can find where the page is there in here somewhere. I've already moved past it. Tell me you took it out of this edition. Okay. Ah, here we go. If your particles of fluid are moving from left to right and see this bump, they're going to have to go around it. If they have to go around it, then what is happening is in order to turn, there had to be a higher pressure here in order to make it turn. Because of that, this pressure is going to be greater than the P, where the P is a perfectly machined surface. So as you go across here, it's essentially just perfect. Likewise, when you're here, you're going to find that this surface will force it to turn, and nature will force it to go back, meaning that this pressure will be less because there's a higher pressure here than here in order to make it turn back to attach to the wall. So this is what I mean by perfect as far as machining. Now again, you're tracking a particle. So we go back to our spot here, and there's movement from left to right. Perfectly machined so it doesn't have to turn. Which means this pressure right here is not higher or lower than its neighbors, it's the exact value. And then if you want to know its pressure, this has no movement. There is no velocity here. So take a look at Bernoulli's equation. Again, if you had no movement, then you could say this is a constant, you could say this. So in fact, the fluid statics and fluid Bernoulli's equation, they have the same element in them. Meaning, I guess you could say the manometer equation is a subset of Bernoulli's equation. So if I want to know P3, well, let's say I start at P4. P4 plus H43 times gamma of this substance is equal to P3. Again, I started, moved down that distance to that fluid. Now, if I start with the assumption that that's atmospheric, or I want to gauge pressure, essentially, P3, this pressure is just the column of water above it. The pressure at the column of water above it. Now this one is slightly different. It is true there's a velocity here. It's true it's a velocity here. But if this particle stops, comes to right here, the particle next to it will go around it. And this one will stagnate, meaning that V2 is equal to 0. Now, if I write Bernoulli's equation between 1 and 2, and he has that listed right there. T1, there is no change in elevation. Now, this term, gone. These are at the same elevation, so they're gone. This is gone. This is gone. This is gone. And so suddenly, you have a pressure 2, which is greater than pressure 1. It's stagnating here on the surface. Now, you can also turn around and say, if I want the P2, it would be just simply gamma of this fluid times the H. I can take this and put it in here, and essentially what I'm saying is I can read these different elevations and back out the velocity. Here's a particular case. Let's say that I want to know the pressure at point 1 using the manometer tube right here. It turns out, and I write this down, pressure at point 1 is equal to this H times the gamma of the fluid. Now, at first glance, you may look at it and say, hey, wait a minute. I'm not seeing something. And what you might question is, all these parallel velocities moving just like so, moving across this fluid, they're all the same values, but they're not turning up and they're not turning down. So therefore, right in here, in this region in here, it's still no velocities. But if you transverse down through here, 90 degrees to this, you'll find that as you go through the depth of water, even though they're moving from left to right, the pressure doesn't change. There's no pressure gradient. In other words, fluid particles not turning. If you were having a situation where they were turning, when going through this, you would have a pressure gradient. So in fact, yes, in fact, this is true. In fact, that is true. And in fact, this is true. What can we do with all those? Well, I can take this part right here and put in here. Take this part and put in here. Let's say we observe that H happened to be 1, the little h happened to be 1, the big H happened to be 2. How fast is the fluid going? Well, I could put on the left side for P1, 1 times gamma plus rho v squared over 2 is equal to, take that one, 2 times gamma, because it's a little higher. So this happens to be 1. So you can move that across, rho v squared over 2 is equal to, move this across, you get this gamma. You realize that gamma is nothing more than rho times g, so you can cancel it out. And you can take the 2 across, and you can say this. Now, what I'll do is instead of just leaving the 1, I'll put a little h tilde here. and you'll realize that's the case. Now, this looks very familiar to you because this is, again, this accentuates the point that Bernoulli's equation is a energy equation, meaning you look back, you drop a marble, you drop a height h, it started at rest, so v top is equal to 0, then you would do mgh is equal to 1/2 mv squared, cancel your m's, move your 2 over to gh, and that would be your velocity after it fell at some point. It's not too uncommon to see this, and once you see it, it brings home the point that Bernoulli is an energy equation, but it happens to be energy per unit volume. Here he's starting to talk about stagnation points, which we already talked about, which is basically, here's a pitot tube, you have a stagnation point here, pitot here, velocity goes right over that. You can use the difference between those two, the difference between this pressure and that one, to pick up the velocity of the flow stream. This is why this is not a great picture, but you'll see every airplane has a pitot tube stuck on it somewhere, either at the point, at the wing, or somewhere. Okay, I talked about that. Examples of use of the equation. So I would say read through this. This is a contraction coefficient. In other words, if you've got a certain diameter, there's a possibility that it might shrink down, and some of it, this being air and this being water. So okay, you already know about m dot, or since in fact the density is going to be constant throughout this part, you'll have a volumetric flow rate, cubic feet per second. You can change that to m dot, or slow, kilograms per second, or slugs per second. However, if you were in thermo, you'd probably do pounds mass per second. That cubic feet per second is pretty common. Okay. So I think at this point, I've just got some problems that I'm going to work for next time. And drop them in there. You can drop them in to one note, and we'll come back and work them on Monday. Here's a good one. What's that one? Okay. That's what I'm going to do for this class. I think I'll just, I'm going to add some papers here. Okay, so I'll do this one on Monday. That's always a good one to see. That's 38. It's the problem statements down here. No, it's okay. It's the problem statement. Good. That's a good one. That's 347. Go and do that one. That one. Let's see if we can do that one. Yep, that's another one. We do this one. I'm not sure we can do all these in that particular day. There's one. Enough, although I want to do one more type. Now, oh, definitely want to do this one, 382. Okay, so I'm looking at this one, jet fuel. Alright, well, okay, we'll just do that. There's two more. We'll do this one. This shows an issue that might occur. Here's basically 1 0. Kind of a difference. I guess that's what I'm going to look at. Maybe that one. Okay. All right. So I think I'm going to sit up and do all these on Monday. I don't know if I'll complete them all, but I may shorten our time right now. did word of the day and everything else, so I think we're gonna call it good right now. A little bit